morning. Today's the fun stuff. Now we're really getting into the fun part of linear algebra. We start studying vector spaces today, which is pretty much the rest of the semester, by the way.
If vector spaces are so useful in Calc 3, why is it not a
Vector
requirement?
space is not Calc 3.
It is?
No, you study vectors in Calc 3. That's just one special type of vector space.
Okay.
The vector space, also known as a linear space. Non-empty set V of objects. We call each object a vector, on which you have two operations: addition and scalar multiplication. These two operations are subject to 10 axioms, 5 for each. If U and V are in V, then U plus V is also in V. This is the closure property under addition. And there's a reason why I'm using the circle plus instead of just regular plus. For all U and V in your vector space, U plus V is equal to V plus U. And so our addition is commutative. For all U, V, and W, the quantity of U plus V plus W is equal to U plus the quantity of V plus W. So our addition is associative as well as commutative.
What does the circle around the plus mean?
It's called circle plus. I'm using that to define my vector addition. It's just an operation, but I'm using that instead of plus so you don't confuse it with the typical addition you're thinking of.
It doesn't get me has different properties than regular addition.
Because I can define addition however I want, as long as it satisfies these properties. So it doesn't have to actually be like 1 plus 1 equals 2 that you're used to. Right? For instance, I could say it's U plus V is equal to U plus V mod 3. So it'd be either 0, 1, or 2 in that case. So I'm just trying to distinguish it from regular addition.
So this would be a whole different type of proving if...
That's where the abstractness comes in.
Because we're just doing like the basic stuff.
For the most part, in this course, because it's an elementary linear algebra course, we're going to be sticking with standard vector spaces like n vectors with the standard vector addition and all that.
Numbers.
We will look at some of the more abstract things, but for the most part, it's going to be standard. Nothing too serious. Right, so far we have closure property for addition, commutative property for addition, associative property for addition. There exists, I'm going to call it E, in V such that U plus E equals U for all U in V. This is called the additive identity, or the zero vector, if you will. This is the existence of an additive identity property. Finally, for each u and v, there exists, and I'm going to call it u bar in v, such that u plus u bar equals e. Right? So u plus u bar is the additive identity. This is called your additive inverse, and will typically be represented as negative u.
So technically, this is completely different than just regular, like,
Well, it's
normal, like it would be called linear space, and this would be called vector space.
no, vector and linear spaces are the exact same thing.
Oh, it is.
Yeah, they're the exact same thing. It's just two different ways of referring to it.
So
I actually don't know which terminology came first.
do we typically work in linear space? Like saying before linear algebra.
Yes. You just don't know that's a linear space.
Okay.
But you're also working in a field. You just don't know what a field is yet. Just study that in abstract algebra.
Is it the same kind of field in calculus?
No. That's a vector field. That's a different field altogether. Now your 10 axioms for multiplication. If u is in v and c is a real number, then c times u is in v. This is the closure property for scalar multiplication. And again, we're restricting our study of real numbers for the scalars in this course. Just bear in mind, it could be a scalar in any field. So we could also be working with the complex numbers. That's a field.
Other than the sets that we like traditionally recognize, are there any other additional sets that have vector spaces?
Well, a vector space is a set. You're talking about fields?
Like meaning as in like real numbers?
Yeah, those are fields. So could do real numbers, complex numbers, rationals are a field, I believe.
Is there anything on top of that?
The quaternions, I believe, are a field. That's above complex. I'm not sure if the octonions satisfy the field. It's been a while since I've done abstract algebra, so I don't exactly remember the definition of a field. So I'm not sure if the octonions would be a field. But I know for a fact the quaternions are. Element of.
Element of the set.
It's in the set. Right, so it's an element of the set where it's in the set. For all u and v in V and every real number C, C times u plus V, C times u plus C times V. So your scalar multiplication distributes across your addition. Across your vector addition.
So is this like the properties that a vector space has to have in order
So
to
these are the
exist?
10 axioms. So each operation has 5 axioms, right? So your vector addition has to satisfy the 5 A's that we just went over. Your scalar multiplication will have to satisfy these 5. For all u and v and all real numbers c and d, c plus d times u has to be c times u plus plus d times u. Got to change that. no idea when it decides to reset the slide, when it just updates it. This is considered the distribution across scalar addition. So your scalar multiplication distributes across scalar addition.
Should the plus inside of parentheses be in a circle?
No.
For notes? No?
That's just addition under scalars.
That's under the additional circle. All right.
So that'd be your standard, like 2 plus 3. So again, another reason why I'm trying to distinguish between the two.
So then what defines addition and scalar multiplication? Is it,
It'll be given.
okay,
So whenever you're given, if you're given a vector space, you have to be given a set along with the definition for addition and scalar multiplication.
does that get reused? Yeah.
Right, so when you're talking about 3 vectors, for instance, the addition is just your standard vector addition that you study, and the scalar multiplication is a standard scalar multiplication that you study. So that's how addition and multiplication will be defined in that vector space. But it can be weird. And we'll see some of that. For all U and V and all real numbers C and D, C times the quantity of D times U is CD times U.
I'm assuming that matrix have something to do with this, like in vector spaces or whatever.
There is a vector space for matrices. So the matrices do form a vector space.
Is that covered in here or like, I'm
Yeah.
trying to figure out why these two run together.
Yeah, we cover that in here. Right, so we do look at the m by n matrix vector space. But again, it's just standard matrix addition, standard scalar multiplication.
So for that to be a space, all that has to be true.
Well,
So
there's
you
one
have
more
to-
as well.
So you have to like think about it.
Oh, the proofs of these are fun. And finally, for all U and V, 1 times U is equal to U. That is, your multiplicative identity is always 1. Those are your 10 axioms of a vector space. Memorize them. Take them to heart. If you will, those are like the 10 commandments for vector spaces. You kind of have to, at this point, unlearn common sense. Right, so a lot of the things that you used to take for granted can no longer take for granted.
So the reason I'm guessing that this came about is that there's like specific things on Earth that have specific properties that need a vector space in order to define it.
Doubt it. Probably more along the lines of some guy just wanted to create something. I decided this would be fun. Generally, how math works is, I say generally, there are a few exceptions like calculus, but math is invented, and then an application is found for it. One of the funniest stories is the person who invented group theory was actually asked about it, and he was excited that he finally found a math that has no application in physics. And then came along string theory, which uses group theory, and that person was not really happy about it. He was kind of irritated. So I think a lot of the math comes about to be like, oh look, it has no application to it. That's just how mathematicians think. We don't care about the application, we care about the beauty. So we'll find something, and we could care less if you can use it. It's cool, it's interesting, let's study it. That's math. Right, so essentially the question is, when am I ever going to use this? Is, who cares? It's sexy. Let's study it.
You're so a nerd whenever you say that.
Sexy?
Yeah.
For every u and v in real number c, 0 times u is the identity, the additive identity. C times the additive identity is the additive identity. And your additive inverse, -1 times u. Right, so again, additive inverse is also represented as a negative u. Again, most of these might seem obvious. Of course, 0 times anything is 0. You have to unlearn that.
Well, yeah, 0 times 0 is
0 times 0 is 0.
Well, I thought there was something like where it's
0 to the 0.
Oh yeah.
You're thinking of that's indeterminate. So I'll go back to your asking about the fields. The quaternions, for instance. You're used to associativity of multiplication. I'm sorry, not associativity, commutativity of multiplication. You lose that in the quaternions. Multiplication in the quaternions is no longer commutative, or it doesn't matter. More along the lines of, think of IJK. I hat, J hat, K hat, and the cross product, the order in which you take their cross product matters. That's the easiest way to think of the quaternions. It's A plus BI plus CJ plus DK. They're not vectors though, they're just IJK. But the concept is identical to cross products. Let V be a vector space. We're going to show these two properties. That K times U minus V is K times U minus K times V. and that u plus u is 2 times u. Let's start with k circle times I'm not going to bother writing the arrows. It's going to get annoying. We'll just take u and v. We know that there are vectors in the vector space. Well, from here, third property, that minus v is actually -1 times v.
Maybe we should switch from using these because they look very similar.
Looks similar, that's why I try to give my u's a tail.
That's worse when you combine with that with the V, and also 4 columns.
I'm just wait, it gets even worse. Oh, well, we know that V is a vector space, right? That means your 10 axioms hold. What axiom was it? M2. That I'm pretty sure is M4. Right? Yeah, M4. K is a real number. -1 is a real number. So M4 lets us write this. Use M4 again. But now that last term would be the additive inverse of your vector k times v. So that first property is proven. Now for u plus u.
So are there like any weird properties that like integers versus real numbers would have in terms of like the 10 axioms?
They all have to follow the same 10 axioms.
Yeah, but like, does the definition of addition change with those?
No. Addition and the scale multiplication will stay the same regardless of the field you're working in. The only thing that changes is where do your scalars come from. That's where the field comes in. So for us, we're only working with the real numbers. And keep in mind, integers are real numbers. Right, so that will all work in exactly the same way.
Is this how you want us to format our answers on tests and quizzes and such? Exams and such?
If this was a test question, I'd actually write out the properties you're using for each step, like I was explaining. Okay. So maybe above the equals, you would write out what you're doing, why you're using it. But otherwise, it would be similar formatting. You always have to explain your step. U plus U. M5. U is just 1 times U. Now what is it? M3? Yeah. M3 allows us to write this. But that's just standard addition in the real numbers. One plus 1 is 2, and so you get 2 times U. So both properties are satisfied.
I know this isn't approved, but are there other ways to get there using different axioms for the first one? Whereas, like most of these, you have to use a specific pattern.
No, so what you could do, so for instance, in this first step here, the first one, I use one of these properties. So you can use either the axioms or any of the proven properties already. For the one that we just did, the U plus U, there weren't any other proven properties we could use. Right, because there's really nothing else that would be helpful for that. So I had to use the axioms there. But any of these, any properties or the axioms you can use, as long as it's been proven already. If you want to use something that hasn't been proven, you have to prove it in your proof.
Yeah, I mean,
Right, you can't just
you can't just
use
say
it.
random stuff. Yeah.
But now, for instance, if there's a test question, you can use this U plus U equals 2U property. Because we just proved it in class. So now you're able to use that property or the property above it. So that's the cool thing about math.
I wish they did this for like elementary algebra.
I prefer not. Only because I don't think at that level,
Yeah,
your mathematical mind is mature enough to
Yeah.
be able to do it. Like I understand, so this gets into the whole Common Core argument. I understand the idea behind Common Core, the way they teach it, the way they do it. I just don't think it's appropriate. Because they're not mathematically mature enough to actually understand that.
Yeah. I think it's really cool that like now as a college student, like all the things I wondered about as a kid.
It's going to start.
Yeah.
And again, that's why, because you weren't mathematically mature enough to really appreciate or understand the proofs. Now, you're mature enough. Now we're going to go, okay, you've now been doing this for a while, but why does it actually work? I remember in real analysis, I had the instructor for real analysis 2, but my friend had him for real 1, and his first day was proving 1 + 1 = 2.
Oh, God.
So he had to actually define what we mean by 1, what we mean by 2, what we mean by plus, and that was how he started the class. And she said it was a really interesting proof, but no one understood it.
Like the integer could be even or odd or.
Right, because again, a lot of them weren't used to that kind of thinking. Because it is a completely different kind of thinking when you get to the advanced math. They say that real analysis is the hardest class you take as a math major. Because it is just a different way of thinking than what you're used to. But then you get through it, you get used to it, and you go, oh, real analysis actually isn't that hard. Topology. Now comes the fun proofs. Proving, well, this one actually isn't proving. Proving to vector space. What we have to do is prove that satisfies 9 of the 10 axioms, which means this is not a vector space. So we're going to prove that all the axioms except for n5 is satisfied. Okay. So again, that's kind of the beautiful thing about the definition. If even 1 of these 10 axioms are not satisfied, it's not a vector space. As we're going to see here. 9 out of the 10 are satisfied, but it's not a vector space because it fails the additive identity. Or not additive, I'm sorry, multiplicative identity.
How would you prove this? You can't use real numbers because obviously you have to prove every single real number for that.
Well, that's what we're going to do. Except we're just going to say that A, B, C, and D are just arbitrarily chosen real numbers. So you're thinking of proof by example, which is not a proof.
Yeah, it's not.
Because you're right, because you have to then show it's always true. But to disprove something, you just need one example. Let's start with A1. So we're going to say, let V equal R2. So those are 2 vectors,
It's just
essentially.
Yeah.
They're writing it as a set of ordered pairs. Same thing as a 2 vector. And suppose AB, comma, CD are in V. I'm just going to write this out. This means that all of A, B, C, and D are real numbers by definition of R2. So this is the definition of R2. Set of all ordered real pairs. And so you can either write it that way. I wrote it that way for the sake of space. Otherwise, it's going to just be absurd. In actuality, it should be this for this course. But just imagine having to write it that way now when you're dealing with R5. It would just, the amount of space would just be absurd. I'm just going to get that out of the way too. Let K be a real number. Now we can move on to proving the axioms. First axiom, closure under addition. And at this point, I'm going into the more convention of linear algebra where I'm not putting circle plus and circle times. It's just regular plus, and that's understood to be vector, the vector addition operation. And k times ab is understood to be the vector scalar multiplication operation. By definition of our vector addition, that's a plus c comma b plus d, right? Remember, we want that sum, so that new vector, a plus b, a plus c comma b plus d, to be in R2. That's what it means to be closed. Well, what's a plus c?
A number. Or a real number.
Specifically, a real number, right? Because a and c are real numbers. The sum of two real numbers is a real number. What about b plus d?
Same thing.
Again, b and d are real numbers. That's why I wrote it up there. Which means b plus d is a real number.
That's interesting how sometimes with proofs, it's like, it kind of leaks into the logic that you have to think about. Like,
So you can always assume the axioms of math to be true. Which is actually an interesting question. Is math a complete subject?
No.
No. Because you're always going to have unproven assumptions.
There are unproven assumptions.
That's what I said. You're always going to have unproven assumptions. Those are called your axioms. You can't ever prove them. But yet we assume they're true to prove other stuff. So math is incomplete. There's actually a proof for that. Someone did actually prove math is incomplete.
Okay, but then doesn't that mean math is subjective at that same time?
Math is what?
Subjective.
Well,
Because you're just assuming.
it would. What's 5?
Well, it's a number.
What's a number? It's something we invented to try and understand it.
I don't know. My whole problem with that is like, what if we all like? What if something changes the whole entire way we look at math, and then everything's proven wrong?
And this is
Well,
why-
that won't ever happen.
And this is why math is applied philosophy.
Actually, math did start as philosophy. Philosophy is actually the foundation of all STEM, not math.
Yeah, it's the
It's-
first.
It's so it is weird. But once something's proven, it's proven in math. Right, so they've actually proven that. Because the thing is, while the axioms can't be proven, they also can't be disproven.
What if someone finds an example that it doesn't work? Then what if?
How long have we been at this? Since at least 0. As long as humans have been around.
How about math starting as a way to barter? I mean, like trade and stuff, and they had to keep records.
I'm not really sure if that would be math
Yeah,
Actually, the
as
mind.
much as just counting.
The minds are pretty good at math.
But as long as there have been humans, there have been math. And we have not disproven the axioms.
Depends if someone did.
They probably get shot.
Like when the person.
Yeah, they'd be in a dark alleyway somewhere and they get jumped by people in the math community. They just get canked. So take that for what it is. So doesn't this satisfy then that vector being in R2? We're closed under addition. A2 is the commutative property. However, AC are real numbers, right? Isn't addition of real numbers commutative?
Yeah.
So I can write that first term as just C plus A. That second term, again, B and D, they're just real numbers, aren't they? And addition of real numbers, commutative. So I can write B plus D as just D plus B, can't I? C plus A, comma, D plus B, isn't that the definition of CD plus AB? Commutativity's been satisfied. Need a new vector for A3, so let EF be in R2 as well. A3 is the associativity property of addition. So that grouping, that's C plus E, D plus F, by definition. So there's our new vector. A, C, and E.
You have to have it.
They're just real numbers, aren't they? Addition of real numbers, is that associative?
Yeah.
So I can group that however I want it, right? For instance, I could group it this way. BDF. Also all real numbers. So their sum is associative. So why not write it that way? And then by definition, that'd be that. Which by definition is that associativity has now been satisfied or established. A4 was what? The existence of an additive identity? What's 0 plus A? What's 0 plus B? So isn't 0, 0 plus AB just AB? 0, 0, is that in R2?
Yeah.
Just found the additive identity, 0, 0. A4 satisfied.
What about natural numbers? What happens to them? Because in some cases they don't include 0. What happens in there? Is there
It would then depend on how, well, it doesn't matter, natural numbers wouldn't be a vector space anyway,
Yeah, it would.
because it wouldn't have the additive inverse. So at that point now, the argument is moot. You don't even need to worry if there's an additive identity or not. But it would depend on how you define the natural numbers. If you include 0, then yes, you have the identity. If you don't, then you don't have the identity. Right, notice that A4 said there exists an additive identity, which means all I have to do is find the vector, which we just did. So that proves A4. And finally, for addition anyway,
Can you go back for a second? Sorry.
1.
Sorry.
So A5 was the existence of the inverse. I think it was supposed to be U plus inverse of U. Not that it matters.
Like in matrix. So if you added the inverse plus the regular matrix, you're saying it would equal the identity matrix?
Different inverse. The additive inverse matrix is different than the inverse matrix.
What's the difference?
One is the inverse A inverse, the other one means additive inverse. To give you the additive identity, which is the 0 matrix. Right, so that's typically why we have to stipulate additive inverse versus multiplicative inverse. Right, so A inverse, the inverse matrix that you typically think of, is actually the multiplicative inverse of A, not the additive inverse. So it's new terminology you have to get used to. But when we deal with vector spaces, there are no multiplicative inverses, right?
Mm-hmm.
So we can just say inverse, and it's known to be an additive inverse.
So that makes matrix.
So if so in the context of dealing with the vector space of matrices, inverse would be its additive inverse, not A to the minus 1. What's A plus negative A? What's B plus negative B? Is negative A negative B in R2?
Has to.
It is, right? So be careful when you say it has to be.
Because 0, right?
In this case, why does it have to be? Because A, B in real numbers, which means negative A and negative B are real numbers. If I go back to natural numbers, is negative A negative B in? Now it wouldn't be. So when you say has to be careful when you say that.
Also, what happens if it's 0? I mean,
Well, what's negative 0?
Yeah.
0. So that's fine. That doesn't matter. And again, that's implied to be the additive inverse. We found the inverse. A5 is satisfied. Oh, good. So that satisfies all the additive axioms. Now for your multiplicative axioms. First one, M1, was the closure property. K times A plus B. By definition.
A plus B or A comma B?
A comma B. I wrote A comma B instead of A plus. Ka, 0. That's the definition of multiplication here. K times A. Well, K is a real number, right? A is a real number. So what's Ka?
A real number.
And clearly 0 is a real number. So that means that Ka 0 is in R2, right? It's closed under multiplication.
I'm assuming that this property is the reason why it doesn't work. Would there be a Cartesian?
The definition is why it's not going to work.
Is there Cartesian? Is there a Cartesian vector space?
Yeah, just the R2 under standard addition and scalar multiplication. Right, so the addition and multiplication you studied in Calc 3, or physics, depending on when you first looked at two vectors. What was M2? Was that the distributive? Yes. That was that one. Which is that, right? That's what AB plus CD is. Now, by definition,
So for this to work, the K times AB is equal to KA times, or KA 0. Wouldn't that mean that B or K has to be 0? Well, it would have to mean B is 0.
no. Because we're defining this to be multiplication, regardless of what B and K are. So it doesn't matter. Right, because we're not saying that the K distributes into the B. We're not saying that. We're saying the K only goes into A and that second component becomes 0 when you multiply. So there is never a K times B. It just maps to 0 immediately. Right, because that's the definition of it. Right, so again, that's where you have to kind of unlearn your common sense. K, A, and C. Those are all real numbers, right? multiplication of real numbers distributes across addition of real numbers? I'm going to do another step. 0. Can't we write that as 0 plus 0?
Yeah.
Now look what we have. Which by definition would be k times a plus b, or a comma b, plus k times c comma d. M2 has been established.
So what would a Cartesian vector space look like?
Just think of two vectors.
Like,
Your scale
what would the
multiplication
property-
would be Ka, comma Kb. That's the only
Okay, yeah,
difference.
yeah.
That would be your scale
That's what
multiplication.
I was sort of trying to figure out.
M3 was the other distributive, right? Distributive across scalar addition. Crap. What do I want to use for the other scalar? L?
Looks like a one.
I'll use the L, ELL symbol. We could have used kappa, but that's a pain in the ass to draw.
Any Greek letter is. Some are easy.
I disagree. Capital Alpha is really nice. Capital Beta is really nice. Capital Kappa is actually really nice. Just looks like Latin K. So why they do that, I don't know.
Mu? Mu's like, okay.
Capital mu, I think it's just U.
Yeah.
I think.
Yeah, it's just a fancy U.
Well, that's lowercase mu. Is that uppercase mu? I think is just an uppercase Latin mu. And I think zeta is the same way. Uppercase zeta, I think, is just the Latin Z. Right, by definition, that's that, isn't it? But again, K, L, and A, all real numbers.
Yeah.
So we know that real numbers distribute. And again, write 0, 0 plus 0. That becomes Ka 0 plus La 0. Damn, I think it's this bad. Man, we've not started yet. It's giving me heartburn. That's not good. we've established M3 property. One more to establish and then one to prove is not established. M4. Oh yeah, that was this one. And then the L again. So that is this, right? K times L times AB. And we have to show that that is K times L times AB. By definition, that would be that, right? LA, comma 0. Now again, by definition of scalar multiplication, that'd be K times LA, comma 0. Kel, L, and K, L and A, all real numbers, which means multiplication is associated. Grouping doesn't matter. So why not group it this way? But now K times L is a scalar. So we can write that. Finally, M5. This is the one we have to show is not valid. This property does not hold. Well, counterexample.
Can you just use any?
No.
Because if B is any number.
There's one number B you can't use in your counterexample.
0?
Yeah. Anything else will work. So let's do my two favorite numbers.
You can do the empty set?
Oh, that's not the empty set, that's phi, the golden ratio.
Oh.
28 and the golden ratio. Now that is clearly an R2, right? They're both real numbers. Yeah. Let's just use the real number. Oh no, I have to use 1. That's right, because this is the additive identity.
What distinguishes the golden ratio from empty set? Like what's the difference of what it looks like?
Empty set's a 0, just with the slash. The golden ratio is a phi. That's the Greek letter phi.
Yeah. Is it like 3 down the center?
No, it is a little arced.
Right.
It is a very slight arc, but it isn't straight up and down. Capital phi is. Capital phi is the circle with a capital I straight up and down.
Yeah, that's probably what I'm thinking.
We want 1 times phi. By definition, that's 28, 0. Which means 1 times it doesn't give you itself, as it should. That's what the fifth property says. That completes the problem. All of the axioms are satisfied with this definition of addition and multiplication, except for the multiplicative identity. In fact, there is no multiplicative identity, right? There's no real number you can multiply a vector by to get it back for every single vector.
Would you be given an example where the basis is not like it's not the main point, but you have to figure out if it's even possible first to do the problem and then go on solving it?
Yes. So I could ask you, right? So I could give you a problem. Here's a set. Here's how addition is defined. Here's how multiplication is defined. Is this a vector space?
Mm-hmm.
Well, of course, in math, there's no such thing as yes, no, or true, false. So if it is a vector space, you have to prove it. If it's not a vector space, all you have to do is provide a counterexample where one of the axioms aren't satisfied.
I mean, like on top of that, then there's like some sort of problem additional to that, if that makes sense.
So what do you mean additional to that?
Like I said, let's assume this vector space, and you need to find, I don't know, the integral of that.
Well, that wouldn't make sense.
Or, I don't know, whatever.
We're not up to that yet. So there are operations in vector spaces. We're not there yet. We'll get there. Those are called linear transformations, which are what we cover after we learn the basics of vector spaces. As of right now, you can't operate on an element of a vector space outside of the addition and multiplication I've defined. We have no other operations yet. We'll study those. The integral actually is a linear transformation.
So there is a possibility that like you could be given a problem, you have to prove that it exists, and then.
So it could be, yeah, prove it's a vector space, and then if it is, perform this transformation on it.
Yeah.
I could do that. Of course, I could make you do three things. Prove it's a vector space, prove it's a linear transformation, and then do it.
Like here?
So I did have two other problems that we're clearly not going to have time to get to because these are really tedious to prove. So this is the idea of the infinite vector. Right, so instead of Rn, right, we have a finite size vector, this is just infinite. Prove that under standard addition and scalar multiplication is a vector space. That shouldn't be too difficult to do. This one's really interesting. This one I really want you to take a look at. The external direct product of U and V. Or of U and W. Right, so if you define a vector space set of ordered pairs U, W, where U is in a vector space U and W is in a vector space W, that is a vector space, and that is called the external direct product.
What's the apostrophe? Is that actually
Prime. So that's just to distinguish it's a different vector.
Okay.
So that's standard notation. So in this case, it doesn't mean derivative.
Yeah.
It's just used to represent a different number. Instead of using a subscript like U1 and U2, we use U and U prime. So that's just standard. So prove that that is a vector space. That one, again, I do encourage you to look at, because that one is an interesting one.
Isn't like vector the third question like the kind of the basis of multivariable calculus? And it's infinite vector spaces essentially.
No, multivariate calculus, the purpose of that is it's multivariate functions. So you have multiple independent variables that affect a single variable. That's more along the lines of what multivariate calculus should be. There's no such thing as infinite space. When I say that, I mean in terms of dimensions. There's no infinite dimensional space.
Yeah.
String theory is 10 dimensions, 9 spatial, 1 temporal. So really, this last one is more just abstract. That one is a very abstract one. But it's just kind of moving on. Extend your notion of a finite dimensional space to infinite dimensional. And it's still a vector space. It still satisfies the vector space properties. Which shouldn't be difficult to see. Right? You should actually be able to see that before you can start writing it out. This one is going to require a bit more forethought. because it's not as obvious as, say, regular vectors.
Is it even possible for the human eye to be able to see? what-
You cannot picture anything above 3 spatial dimensions.
like,
Not possible. Because we're not.
Is there any way to?
So what we do is, actually, if you go to the tea room in the math department, I think they still have the visualization of a hypercube there. So we kind of visualize the shadow of a hypercube as the hypercube, and it's like a cube in a cube, kind of, with connections on the corners, all the. That's kind of the only way we can imagine 4-dimensional space, is what would its shadow in 3-dimensional space look like. Beyond that, there's no way. Because 5-dimension would be, you'd have to do a shadow in 4 dimensions. But we can't even picture 4 dimensions. But again, that's just a shadow. What does a hypercube actually look like? We have no idea. And we'll never be able to. Sadly.
I feel like a hypersphere would be easy.
Hypersphere is the same thing. No, it's a lot harder. Even trying to visualize the shadow of a hypersphere is pretty difficult.
Isn't it just a sphere?
So project 3 should be up now. It is a hill substitution cipher. It's a really interesting project, a good application of comp sci and encoding, encryption. Right, there are 2 homeworks. We will look at subspaces on Thursday.